Alright, welcome to our last video of Unit 6. This is Le Chatelier's principle, which is by far the hardest principle, just saying. So, here we go. Not to scare you. Le Chatelier's principle basically states that a system in equilibrium will oppose a change in equilibrium in a way that helps eliminate the change. In other words, if a system is at equilibrium, if that equilibrium is disturbed, my phone keeps buzzing, it's kind of freaking me out, then the system will act in such a way to reach equilibrium again. Okay, this is like if you're riding a bike and you start to fall, you try to stop falling. This is if you're tripping and you start to fall, you try to stop tripping. I don't know why I'm obsessed with falling. This is if your grade suddenly drops and you don't like it, you try to fix it. This is obvious. This is when something wrong happens, we try to make the wrong stop happening, or we try to fix the wrong. So if you're actually an even better analogy, are gymnasts, because we have the Summer Olympics this year, I think. I think it's summer. I'm going to pretend it's summer because I know it's summer. You got those people who are like crazy awesome at balancing. And if they start leaning, so you got a person balancing and yay. If they start leaning to the right, they try to fix that by leaning back to the left. And their goal is to stay in the middle. Or if they start falling this way, then if they fall this way, they're like that. But if they fall this way a bit, they try to come back to the middle. That's Le Chatelier's. It tries to stay at equilibrium. So, for chemical reactions, this matters most in terms of changes in concentration, which again deals with molarity, temperature, and pressure. And most of your time in Le Chatelier's problems, I will say, if we change this concentration or we change this temperature, what's going to happen? So, let's start. All right, first off, when we change concentration, basing an increase in concentration on one side will cause a shift towards the other side. So, basically, if we have, we've got a board that's balanced, okay? Here's the analogy. Our goal is to stay like this. I'm going to say that again. Our goal is to stay like this. And you know what? Why not? I'll say it one last time. We're trying to stay at equilibrium. Okay? So this says that if I suddenly put, let's say, an extra block on this, that's going to make my thing start, tilting because now it's heavier. If I want to stay at equilibrium, I'm going to have to basically either get rid of some of this or put some more over here to bring it back up. So, again, if you're starting to fall, go this way, you're going to try to move to go back this way. You're going to try and fix things. So, in terms of concentration, if we have too much on one side, we try to take some of it and put it on the other side. Or if we have a decrease, if we have too little on one side, we try to move some over from the other side to balance this out. It's basically you're trying to keep things balanced. So, changing in temperature. For an endothermic reaction, so basically something where delta H is positive, our heat will typically be a reactant. And for exothermic, again delta H, our heat will be a product. Because for endothermics, you're requiring energy, so reactant. Exothermics, you're producing energy, product. Okay, once you've got that established, changing temperature comes exactly back to changing concentration. So if heat is a reactant, you're changing the concentration of a reactant. If heat is a product, you're changing the concentration of a product. And just go back to what you did in the previous one. Okay. Last thing, though, you got to remember for temperature. If our temperature change increases reactants, our K will decrease. Where if it's for some reason it's not up there, but a increase in products, our K will increase. Because keep in mind, our K is represented by our products or reactants. So if we increase products, our K gets bigger. If we increase reactants, our K gets smaller. Or vice versa, if we decrease products, it gets smaller. And if we decrease reactants, it gets bigger. So that only again changes with temperature. We won't change our K for concentration. It's only going to change with temperature. All right. Last change is pressure. An increase in pressure is a little weird one. will shift the reaction towards the side with the fewest number of molecules. Now, this technically only really deals with gases, so they won't ask you. But for the future, this only applies for gases. So, increased pressure, you go to the one with the smallest number of molecules. And what you're doing is just counting up the coefficients. And a decrease in pressure will shift towards the one with the largest. And again, you're counting coefficients. So, that's pressure. Okay, finally, let me tell you some terminology that for some reason I didn't underline. Sorry. If a reaction shifts to the right, if I use that phrase, that means reactants are being converted into products. So shifts to the right means stuff is going to products. So that will decrease my reactants and increase my products. Okay, that's the phrase shifts to the right. If a reaction shifts to the left, then I'm going to increase my reactants and decrease my products. So just the opposite. All right, so for the reaction below, we got to indicate what direction the reaction will shift when the indicated disturbance occurs. There's your reaction. Okay, I'm going to let you try for about 2 minutes, maybe just one. I want you to think through a couple of these. Key thing you got to note, though, this is exothermic because our delta H is negative. Your notes talk to you about what exothermic happens. So try these, see what you got. All right, so if I decrease hydrogen sulfide, that is a reactant. I now have less reactants. Okay, I'm trying to tell you which direction I'm going to shift. If I have less of one side, I'm going to shift towards that side, which means in this case, I'm going to shift to the right or the left. Okay, if I increase the pressure, I'm dealing with coefficients. I have 3 molecules over here, 1 plus 2. And I have 5 over here, 1 plus 5. 3 is less than 5. That means if I increase my pressure, I'm going to the left. Okay, if I increase the temperature, this is exothermic, which means heat should be a product. If I increase products, then I'm going to shift away from them. If you have too little on one side, you shift towards it. If you have too much on one side, you shift away from it. So this says we're increasing our product, which means we're going to the left. I don't know why these are all going to the left. These are literally all going to go to the left. Wow, that's really boring. If I increase CS2, I have too many products, so I'm going to move it to the left. If I have decreased CH4, I'm going to have too few reactants, so I'm going to have to make more and go to the left. Now, they honestly don't always go to the left. That's really kind of funny, actually. Sorry about that. But that's kind of Chatellier's principle. Okay. Lastly, I want you to try and figure out what's going to happen on the position, what decrease in the temperature will do for the following equilibria. Basically, you're telling me if I decrease my temperature, what direction is it going to shift? Okay. However, I want you to also tell me what our equilibrium constant is going to do. So, try it. Come back in a bit. Okay. So if I decrease temperature in this reaction, I'm decreasing a product. Means my equilibrium will shift to the right. Shifting to the right means I now have more products, so my K will increase. Okay, in this one, we're endothermic, which means it's a reactant. If I decrease a reactant, I need more reactants, so I shift to the left. And if I have more reactants, my K is smaller. Finally, in this case, it's exothermic because it's negative. That means heat's a product. If I decrease heat now, I have less products, so I need to go to the right. And if I increase my products, my K will increase. I really don't know why I keep drawing them like that, but whatever. There you go. That's Le Chatelier's principle.